Hello everyone, welcome back to this video. In this video we are going to have a look to exponent laws. So we have a look on different concepts behind exponents. Once again, you have to remember there's exponent laws. However, since this course should teach you how to get better at math, I want that you do concept proofs, meaning you have to prove the concept behind those things. And only if you understand the concept, you will actually advance in your mathematical journey, because those things are the beginning. In the last video we talked about the binomial formula and why it is true. We did a concept proof there as well. As I said, a lot of the videos, especially in the more easier level, are being concept proofs. I'm planning to do a course on linear algebra. There we will do actual proof, mathematical proof, and I will do a course on mathematical language. Although this is a lot which you have to study, I try to give you a small introduction. I will also want to apologize. I said, for example, this 2 to the power of 3. In the last videos I said 2 times 3. Of course this means 2 to the power of 3. I'm sorry, as you may hear, I'm not a native speaker. So let's begin with the first exponent rule. A to the power of m times a to the power of n is nothing else than a to the power of m plus n. Give a concept proof why this is true. I'm going to wait 3 seconds, and this time you can pause the video. If you don't have any idea, just watch the solution. But as I said, you should understand the concept. So welcome back. Let's just have a look what is happening. So a means that the base, so a means in this case this is the same number as this. So a is equal to a. So those are not random numbers, so those are equal. So we can do an example. Let's say 2 to the power of 3 and 2 to the power of 2 equals to 2 of the power to 5. Oh my god. So let's see if this is correct. 2 to the power of 3 is nothing else than 8, and 2 is nothing else than 4. This is nothing else than 32. So this is nothing else 16 times 2, so this is nothing else than 32. So this seems to be correct. Let's see why this is correct. What I like to do is to think what an exponent means. So if we have, for example, the exponent of 3, this is nothing else than 2 times 2 times 2, right? And now we have to believe we are multiplying this with, let's say, 2 times 2. So now what you will see is I'm sorry, you don't need brackets, I'm sorry. So this is the thing what you get. And let's count. 1, 2, 3, 4, 5. So this has to equal to 2, 5. This is like the basic concept proof, just understanding what an exponent actually does, and this is like saying how many times you multiply the number by itself. And of course, if you could say, for example, this would be 2. Yeah, as I said, this would be 2 times 2 times 2 times 2 times 2. Then you could those and times, and then it's just this. If you want to do under this logic, but you are able to like combine those things. So this is general concept proof for this. Pretty easy. This is like standard. Whereas in my opinion, it's not even easy, but it's like beginner mode. So this is very easy. We're getting to another idea. am divided by an is nothing else than a to the power of m minus n. Why is this true? Pause the video, 3 seconds. So let's, for example, just take the same thing. We have 2 to the power of 3 and 2 to the power of 2. So after the exponent rule, this means this is 2 to the power of 3 minus 2 equals to 2, and this is nothing else than 2. So why is this true? Just see what division means. So we have this divided by this. The only thing you have to do is this, and what you see is the pattern actually from the exponent, because you're able to say this is nothing else than 2, 3 and 2, 2. 2 to the power of 2. This is going to be 1, so you removing those, and this is 1. And what you see here, this gets to 0, okay, because you have 2 times 2, and therefore this rule applies, and this means this is equal to 2, therefore it's correct. So, oh, this is very nice. Constant proof of a to the power of m to the power of n. 3 seconds. Okay. Pretty easy idea is, again, let's say for example we have 2 to the 3, doesn't make any difference. This means it's nothing else than 2 times, to the power of 6. Why is this true? Okay, imagine you have 2 and 2, and this is times 3. Now we actually see the same idea like before gets, so this is nothing else than, let's say, we're going to just expand, so this is nothing else than this times this times this. And let's see, since all of this is multiplication, we actually just can say this goes away, this goes away, this goes away, this goes away. So what we get is 1, 2, 3, 4, 5, 6. And that's the reason why this exponent rule is true. Okay. So the general idea behind this is just to expand. I'm sorry again, I did like, but you don't have this is actually wrong. You should do this to get another result. I'm sorry. Do you? Oh. So, AB to the power of m is nothing else than am times AB, then b to the power of m. Why is this true? 3 seconds. Right, so same idea here. Let's for example say we have 2 times 3 this, which means this is nothing else than, we just can plug those together and those, and this gives us this. Right, and this is like the concept behind this. We could do this with numbers here. Let's say for example we've got AB times m. This means this is nothing else than AB times AB times m times, so with the exponent of m. And then you just plug those together, and you see if you have m here, of course you just can combine a infinite, so it's just a simple combination. Let's say for example you have 2, then let's say we just stick with the b, then this means here you will have b2 as well, then here you will have to be 2 as well, to the next you will 2 as well, 2. So the exponent just says you how many 2's you will see. Same idea with the b, and then you just combine them. So why is a to the exponent of 0 equal to 1? There I give a concept proof as well. This might be a little bit difficult, but you can find a solution for this. It may take some minutes, so yeah. So welcome back. The proof of this is actually pretty easy. So let's say for example you've got am divided by a let's do real numbers because I would have to do am as well. Let's say for example this. Alright. This means nothing else. Let's expand this. So 2 divided by 2 times 2 times 2. Okay. Now we just can say, okay, this goes away, 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 and what we're left for is 1 over 1, which is equal to 1. Okay. But we know from our from this rule that this is nothing else than 2, 3 minus 3. And this is equals to 2 over 0. To the exponent of 0, I'm sorry, to the power of 0. So, and that's about it. This is the concept proof. Yeah. As I said, just remember, a to the power of minus m is nothing else than 1 divided by m. Sorry. This is like the idea. Why is this true? This might be a bit difficult to understand. It's the reason why I'm going to plug this in the next video. We're going to prove why this is true, since I find this proof is actually pretty interesting. So, but just remember this. Let's take an example. You've got you've got x minus 3. This is equal to x 3. Okay. Nice. This might be the most difficult of those all, and this is the concept proof of NAM. Let's try to see if you get the idea. We see us back just in a minute. So the idea behind this is quite easy. So I solved this pretty fast. I actually didn't have any examples, so I just figured it out real quick. So my idea behind this is quite easy. Let's say you have 3 to the exponent of 2, you get 9. Let's say you divide this by 2, then you get 3 divided by 2. We know this is equal to 1, so it's 3 to the x to the power of 1. And since we have to do the same operation on this side, this gives us that 3 is equal to that 3 is equal to 1. So this is like the square root. So this is the definition of the square root. If we would plug in the square root here, this gives us and this is okay. I think the idea behind it is clear. Let's do this with the example with this. So 2 to the exponent of 4 is 16. Divide both sides with 2. Then we get 1/2, and then if you then this is nothing else than 2, then it's 2 to the exponent of 2. This is nothing else than 16/2. This means 4 is equal to 16/2. And as I said, 1/2 in our understanding is like the square root, but in this case you wouldn't have to need the square root, because this is enough for a proof, because you said 4 is equal to 16/2. Okay, so let's understand really what the concept behind why this is nothing else. I mean, after a rule, let's have a look to a rule real quick. We know a to the power, so a to the power of mn is nothing else. Then you see here the nth root to the power of m. Let's see. Let's use our example for this. What is this? Let's see. Okay, this is from the last video. Let's use our example 8. Actually, I was quite surprised. So I took 8 to the power of 5. I didn't know if this would be squared by the root of third, but it did. So I used a calculator for that. So I was surprised. It was like the first number. I don't know. I just wrote it. It wasn't actually about like the if it's like a nice number, but anyways, go on. Let's go on. So we know 8 to the power of 5, as I stated here, equals to 32,768. So if we know, for example, say we divide both exponents by 3, this gives us 8 to the 3rd. So we know if we would use this, this would be nothing else. I'm sorry. This would be nothing. Oh, Jesus Christ. This would be nothing else than the square root of 3. This makes sense. As I said, we wouldn't need a square root because we are already proving this, because this is always equal to each other. So we wouldn't need a square root, but just to understand the concept, what we are doing here. So then we know here, this is the 3rd squared root. And what we get here is actually 32. So we know 8 fifth third is equal to 32. We just get away. We just get back. We just like deleting the 3 and the exponent. So we just multiply the exponent by 3. Of course, we have to do on the same. We have to do the same here at this side. So we know 8 fifth equals to 32. 32 third. This is correct. you can plug it in. I just am going to calculate it again. A to the power of 5 gives us 32,000, and 32 to the power of 3 gives us 33,000. Therefore, and then we just plug it in, the third root of a to the fifth gives us this. Okay. That's the reason why 8 to the fifth to the power of 5 divided by 3 is this. Okay, because of this step here. That's it. So, as I said, this may be the hardest, but it's not that. Yeah, it's not that. Yeah. At the end, idea, because this is extremely important. You can't say 2 divided by 0 or 3 divided by 0 or pi divided by 0. This is not possible. You can't divide by 0. No number a is divided by 0. And just to understand if you, just to see if you understand the problem, prove this by concept. Yeah, pause the video and then we see us in just a second. So, if we say a divided to 0 gives us any number, let's say x, we can use our normal understanding of let's just say, for example, 2/3 equals to x. So you just multiply here times 3. So this gives us 3x. Okay, then you could divide by 2. So divided by 2. Divided by 3. I'm sorry. In this case, divided by 3. It's getting late. So this would give us 2/3 equals to x. Let's see if this is true. So if we now would say, yeah, it is true. I'm always saying this. I'm confused sometimes. I'm sorry. Yeah, it is true. So this is like the idea. If we now would say we've got a divided by 0 equals to any number x, this would mean we could multiply this by 0. You know, because this is like the basic rule to get rid of this. We just multiply by 0. So let's do this. Multiply by 0. A equals to x times 0. The problem is x times 0 equals to 0. So a equals to 0. So this gives us a big problem, because this would mean there is no that every number a is equal to 0, and this is not true. So there's only one. I personally would say there's only one correct, and this is 0 divided by 0 equals to 0. Right? But let's say, for example, this, you can divide by 0, you get a number a. You could say you multiply by 3, so you could say 3 equals to a times 0 and 3 equals to 0.